Okay, so we're going to continue with part 2 of 11.10, and what we ended with was that given f of x being e to the x, the Taylor series was x to the n over n factorial, where n started from 0 and went to infinity. So what we want to check is, why does this equal e to the x? Because our hope is that that actually does equal e to the x. So the answer comes from first considering what's called the nth order Taylor approximation. So this is just basically the first n terms. Let's just now come to a general, we'll come back to that example in a little bit. So this is a general Taylor approximation where we just take all terms up to the nth order derivative. Okay, so this is called the nth order Taylor approximation. So note that the limit as n goes to positive infinity of t sub n of x, that is exactly the Taylor series T of f. So what we want is that as n goes to infinity, the difference between f of x and this nth order Taylor approximation should go to 0. Because as n grows, you're getting closer and closer to the actual full Taylor series. And if that equals f, then that should get smaller and smaller and smaller. It should go to 0. And so I'm just going to state a theorem which I'm not going to prove. It involves the mean value theorem, and I think the proof may be a little bit too much at this point. You can check out, at least some part of it is in the book. So the theorem is as follows. So suppose f of x is infinitely differentiable. Near, well, instead of saying near, let's just put a practical interval on an interval a minus r, a plus r. Okay. And so let r sub n of x be f of x minus t sub n of x. So this Rn of x, we call this the remainder, the nth order remainder. I'll just call it the remainder. So what we want essentially is, that this remainder goes to 0. But it actually turns out there is a little bit more we can say. This remainder is actually, so let this x value, by the way, is going to be somewhere between a minus r and a plus r. So x is an element of this interval. Then the remainder here is it actually depends on the next term, the n plus 1th order term. And let's call this c, x minus a to the n plus 1 over n plus 1 factorial. For some c in a minus r, a plus r. Okay, so this remainder actually depends on some c which is located between these, somewhere inside that interval. And so, well, if we want, what we want, so that's what the theorem says. What we want then is that the absolute value of Rn of x goes to 0 as n goes to infinity. Okay. Well, let's check that that actually happens for, so we're going to check using this theorem that this happens for our example for the Taylor series of f. Okay. Now, if this does happen, okay, i.e., so we're going to check that this happens for t of f where f of x is equal to e to the x. So if indeed we can show that the remainder goes to 0, then that would mean that indeed the Taylor series that we found is actually equal to e to the x. That's the whole goal of this. And this whole remainder portion, I'm not going to emphasize you guys actually computing remainders. You can spend time on that separately if you'd like to. But I want to do at least one example of this so that you've seen it. I'm not going to test you on it, but I would like you to have seen it. Okay, so let's take an n plus order remainder. R sub n of x. This depends on so let's fix an x, by the way. So fix some x value. Because remember, this series converges everywhere. So we're going to fix any x value. Our interval where this thing converges is the whole real line. So let's just fix any x value and say, okay, R sub n of x depends on the n plus 1th derivative of x. Well, all the derivatives of f are just e to the x. Now, we know that R sub n of x, this is equal to e to the c times x minus 0. Remember, a was 0 for us. We centered at 0 to the n plus 1 over n plus 1 factorial. Now, this e to the c, well, this c is going to be somewhere between, so c here is, so I should have stated this a little bit more clearly. It's actually between, let me fix this. This interval, it's actually between, somewhere between x and a. So let me just adjust this slightly. So this c is actually some c between x and a. Okay, so in this case, c is between 0. Let's just assume x is positive. It doesn't really matter. 0 and x. Okay. So this, remember, this x is some finite value. So this number e to the c, this is at most. So e to the c in absolute value is less than or equal to some number, let's call it m. Okay, so for example, if x was, say, 10, e to the 10th would be, as we would choose e to the 10th as m, something like that. Okay, so this term, the key point is this term is bounded. So since that term is bounded, we have r sub n of x being less than or equal to m times x minus 0 to the n plus 1 over n plus 1 factorial, which is m x to the n plus 1 over n plus 1 factorial. Remember, x is a fixed value here. So So we could choose, by the way, here, m might equal e to some, say, x plus 1, for example. Fix some x value. We're going to assume, for now, just that x is positive. It's a similar thing if x is negative. So, so here now we have that r sub n of x is bounded by this quantity. And we want to show that the limit as n goes to infinity of r sub n of x is 0. We want this. Because if that's true, then the Taylor series actually equals the function. But that is true. What happens here? If x is fixed, so if you have mx to the n plus 1 over n plus 1 factorial, this thing, m is just a constant. This is fixed, so this actually equals 0. Okay. All right. So I know that was kind of a lot, but this is how you formally show that that the Taylor series actually does converge to the function. So in conclusion here, we have that e to the x is actually equal to x to the n over n factorial for all x. And this is called the Taylor series or Maclaurin series of e to the x. Guess we'll write it. So this is the Maclaurin Taylor series of e to the x, and which is kind of nice. This is just a giant polynomial. So if actually to compute e to the x, a lot of calculators, I would imagine, I don't know for sure, but they could actually use this as an algorithm to compute e to the x. Okay, so what I'm going to do is I'm going to leave you with a little exercise, which we'll do next time. We're going to not worry about the remainders part. We're just going to assume that the remainders do go to 0 and everything converges nicely. So find the Taylor series of two things, sine of x, cosine of x, centered at 0. Okay, so we'll do those next time, and that'll be, we'll have probably just one more video on Taylor series after that. Okay.